happens is that as per our syllabus, we are basically having 5 types of diodes that we are going to diode names. Okay, so the first diode that we are going to check is a Varactor diode, and today probably we are going to discuss about Varactor and Zener diode. Okay, so second is uh, Zener diode. Okay, and we are also going to talk about Schottky diode. Although we have already studied a bit about it, metal semiconductor junction, still we are going to study a bit more about Schottky diode. Okay, and then we have got the tunnel diode. Okay, and that is also important. And finally, something which you already know, light emitting diode. So we're just going to talk about these diodes specifically, okay, because that's important. And what we're going to do is we are going to probably just draw the symbols here, because before we start, it's important that we all know what are the symbols of different diodes. Okay, and there is certain idea about how the circuit works based on the symbol that we are going to talk about. Okay, so if we just specifically look into a Varactor diode, okay, it looks something like this. Okay, it looks something like this, and all of these diodes are actually basically taking this simple diode circuit. This is the diode symbol. Okay, but this is a normal PN junction diode. Depending on whether a diode works in reverse bias or forward bias, okay, based on this, we are actually going to have different symbols. So a Varactor diode basically works on the principle of capacitance, okay, and this is the symbol that it has, okay. And what happens is that these diodes, we have to know whether they work in forward bias or reverse bias. For example, Zener diode is something which you already know works in reverse bias, okay. So some of these points should be already known to us, okay. So we can in general consider it to be a bit of revision. Apart from that, we are also going to look into some new facts about these specific diodes, okay. So Zener diode, you know, it will basically look like a Z, okay. So maybe we can just draw the Zener diode now, okay. So a Zener diode will look like this, okay. And the symbols are important because I have seen in some entrance exam they will give you 4 options of different symbols, and then you have to just tell what is the exact symbol. Okay, so this is the Zener diode. Okay, and then we have got the Schottky diode. The Schottky diode is something like similar to Zener diode. Okay, so it is something similar to the Zener diode. What happens is this. I'll probably just copy this Zener diode and tell you what exactly a Schottky diode looks like. Okay. So you know this is Zener diode, okay, and what happens is a Schottky diode is slightly more bent, okay. So if we just to consider a Schottky diode, just take it here, move it like this, and move it like this. So you can say it's like an S, okay. So it's like an S, okay. So that is actually a symbol of Schottky diode. Okay? And then we have got the tunnel diode, right? So tunnel diode, what happens is just again copy the same thing, okay? And okay. Okay, so what happens in basically finally the tunnel diode is we are just going to have a symbol where both the sides are actually opposite. Okay, just right here. Yeah, so I'll use the eraser and also practice it. So in our tunnel diode we have it bent in this direction. We have it bent in this direction. Okay, so that's important. And finally the light emitting diode. Okay, and light emitting diode something like this. Just a sec, give me a moment. Just correct this. And one more thing is like whenever you open any kind of electronic circuit, you sometimes actually are able to see even those different kinds of diodes. Okay, so how do they look physically is also important to know. Okay, and in a light emitting diode, what happens is the light is getting emitted, right? So what happens is we are not going to we are just going to draw a simple diode. Okay, and then what we are going to do is we are going to show some light getting emitted. So you can either show it at the bottom or at the top, doesn't matter. Okay, so the light is getting emitted. So this is a light emitting diode. On the other hand, if you consider something like a photodiode, you will have a symbol where the arrow goes in, okay, because light falls on it and the diode starts operating, okay. So what I'm going to do is I'm just going to show you the different looks of the diodes, okay. But I hope it stays on the screen because sometimes this is actually showing some kind of error. Okay? So uh, show you some diodes. Okay, I think this will be interesting. So the first thing is Varactor diode. So Varactor diode actually looks like this. Okay, so if you actually open a circuit, okay, and you look into a Varactor diode, you actually see these kind of diodes, and that means there is a Varactor diode. So it basically works on the principle of capacitance. Okay. And then we have got the Zener diode. I think Zener diode is also something which is shown very common in devices. Okay, and basically it can be used as in a voltage regulator. Okay, so a Zener diode actually looks something like this. Okay, this is the look of a Zener diode. Okay, and when you look into a Zener diode, you see that on one end you are basically going to have a dark portion, okay, that is actually representing the negative side of the Zener diode, and light portion will actually represent the positive portion. So that's the anode and that's the cathode. It's very important to identify, okay. Whenever you are actually looking into the symbol of a diode also, you know that the plain portion is basically a positive part, the anode, and the side where there is a straight line or a bent line and so on, depending on what kind of diode you are talking about, you have got the negative sign. Okay, so that's how a Zener diode looks like. Okay, how does a Schottky diode looks like? A Schottky diode looks like something like this. Okay, okay, so I think again this app showed an error. So as soon as I'm importing an image, it's showing some kind of error. So I think yeah, okay. File was big, so it took some time. Okay, so this is a Schottky diode. Okay, so these are actually all Schottky diode. This is how a Schottky diode looks like. Okay, so you can look into this these kind of circuits, and if you have these kind of diodes, is basically a Schottky diode. Okay, so we're going to look into that also. And these are actually a different version of Schottky diode. This is more common in circuits. Okay, here also this side will represent the negative and this side will represent the positive side. So we're going to look into this specifically when we are going to come across them one by one. Okay, so that's Schottky diode. Next we have got the tunnel diode. Okay, let's see how does the tunnel diode looks like. Okay, so the system is not supporting that anyway. We'll just so different kinds of diodes and how look is important because we might be actually using them. Okay. So if you look into an image of a tunnel diode, this will actually look something like this. Okay, you have a more of a metallic structure. Okay? You have more of a metallic structure, and this is exactly how a tunnel diode looks like. Okay, so this is the image of a tunnel diode. So you know the tunneling effect, which we know in quantum mechanics, these kind of effects are actually applicable in tunnel diode. Okay, and then finally we have got the light emitting diode. So light emitting diode, I think all of us know. Okay, how does it look? Because more common. Okay, we are actually even using it, and you know light emitting diode uses a voltage of approximately so these kind of diodes are quite common. You might have already seen these kind of diodes. Okay, so light emitting diode approximately uses 1.5 to 3 volts. Okay, so if you are connecting it with a 12-volt battery directly, you're going to get damage that light emitting diode. So most of the times, whenever you are drawing a circuit for a light emitting diode, you are actually connecting a resistance in series, okay, to lower down the voltage. So that's also very important. So light emitting diode is a kind of revolution that has come across because nowadays LED actually has reduced the energy consumption to a very drastic level. Okay, so that is very important to know about light emitting diode. Okay, so what we are going to do now is we are going to talk about varactors. Okay, so we are going to talk about varactors. So the topic for today or now is varactors. Okay, so I'm just going to give you some important points on varactors, and then you're going to understand it better. I think it's important. So let me just increase the size because that's the heading. So probably today we are going to cover with varactors and Zener Diode, and we don't have too many long slides. Okay, I'm not going to go into too much detail of these diodes. Okay, because these things are already known to you, and I'm just going to write down some specific points which will be very important for you. Okay? So what happens in a varactor is we are actually having a variation of capacitance. Okay, and once we actually do the biasing, forward bias or reverse bias, we are going to get different capacity of the varactor. Okay, different capacity of the varactor. So that's exactly what we are going to do. So this is basically a special type of PN junction diode. Okay, just reduce the size. Okay. So please note down these points. Okay, this is very important. Special diode. Okay, special type of, maybe we can write down PN junction diode. One point to remember. Number two, it has got the capacitance property. Okay, capacitance is controlled by reverse bias voltage. Reverse bias voltage. Okay, so that is important. Okay, and what happens is what happens when the diode is forward bias. Okay, so when the diode is forward bias, current will actually flow through the diode. Okay, it's not that it doesn't work in the forward bias, but its capacitance can be controlled in the reverse bias condition. Okay, so what happens is when it is reverse bias, okay, uh, we do have a high resistance depletion region. High resistance depletion region exists. Okay, and number four also works in forward bias. So it works like a normal diode in forward bias, but then in reverse bias, basically its application lies where we are basically using it as a capacitor. Okay, so that is very important. Okay, and it has got some specific names. Okay, I should just take a different point altogether. Some more points which are important. This is also called variable capacitance. Okay, capacitance. So something like a regulator. Okay, voltage regulator, or you can actually consider something like that LCR circuit where you can actually control the circuit by varying the capacitance. Okay, so that is called a variable capacitance. So the controller of your fan, the speed of the fan you can control. What exactly we do there? We do actually control the speed of the fan by controlling the current that flows through it, and this can be actually done by varying the capacitor. Okay, so that is a different kind of capacitor altogether. There is a variable capacitor, but then a varactor, which is actually having diode property, is also can be used as a variable capacitor. It has got specific application. Okay, so this is called a varicap diode. So don't get confused if some other name is given to it. Okay, you should be able to do it. Okay, this is also called voltage variable capacitor, VCC type. And the other another name for it is tuning diode. So you can actually tune the circuit. Okay, you can actually control the amount of current that flows through it by tuning the voltage that is being supplied to the diode. Okay, that's possible. Or the one more name is there, which is basically called as the variable reactance diode. Okay, so that is important. And since we already know the symbol, okay, but then let me, I think since we're doing it, so just draw it once. We have got different ways of representing it. Okay, so just draw the figure like this. So this is your capacitor. So you have this, and now you understand why there is a symbol like capacitor in front of this. Okay, and whenever you're actually having a diode, on this side you always sorry, on this side you always have the anode. Okay, already have the anode here on this side. Okay, this is your anode, and then on the other side you have got the cathode. Okay, so this side So anode and cathode, we already know about it, right? So how does it operate? Okay, so basics of operation, probably we can just study a bit of basics of operation here. Okay. So I'm just going to give you a basics of operation, few sentences probably. Okay, basics of. So if I take a real class, I'm basically going to just write it on the board. So I'm just trying to do the same, okay? Because if I make a presentation and all, it takes a lot of time also. So I think all of you can do it together. It's very important. Okay. So the very first point that we should know about this operation of a varactor is it works in reverse bias. Okay. Reverse. Okay. And this will actually give rise to three regions. Okay. So what are those three regions? You already know. Basically, you have the two sides. Okay. Okay. Every time this board is crashing, probably have to resort back to some other software. But anyway, sharing stopped. So a Varactor diode will basically work in reverse bias. Okay. So works in and gives rise to three regions. So even the depletion region can be considered, okay, rise to three regions. You basically have got three junctions, okay, one on the other two sides and one on the depletion region, okay. So what are those three regions, okay? So at either end, okay, the P and N regions, okay. So this is a PN junction diode, okay. So don't consider the Schottky junction that we talked about yesterday, okay. At either sides, okay, on the P and location ends. Let's write down P and N ends. Okay, that's there, okay, and the depletion region. And so depletion region is a region where there is no current carriers. Okay, depletion region we don't have any current carriers because there we have got the electron hole pairs. Okay, which are actually sitting there tight. They are not able to move. Okay, that is something which you already know from the basics of diodes. Okay, so no current carriers we have here. And whenever you are basically considering a capacitor, okay, you already know about capacitors, I guess, but then let me just give you this basic thing here. So whenever you are actually having a capacitor and you want to measure the capacitance of a capacitor, okay, you want to measure the capacitance of a capacitor. How do you measure it? You basically write down this in this way, okay. C, yeah, just a sec, just connect my pen. So in a capacitor, you basically know the relation is this, okay. C is equal to epsilon naught A divided by D. Okay. So these regions will actually give you what is A, okay. And then this distance between these two plates will give you D. So if I'm saying that this acts like a capacitor, there should be something similar to it, okay. So this D within this region, we actually have got the dielectric, okay. If you remember the dielectric or the insulators, okay. So dielectrics are slightly different from insulators. If you actually apply an electric field, there are certain different behavior compared to a normal insulator, okay. But in general, we can say dielectric or insulators are there. So what is the insulator in this variac? The insulator in this variac is nothing but the depletion region. Okay, so depletion region will act as an insulator. So we can actually compare it with a capacitor. Okay, and we can say depletion region acts as a insulator. Okay, so that is important. And number 4 might be we can talk about the plates. Okay, same as capacitor construction. Okay, so like let me write down same as capacitor construction. Okay, and then it has got conductive plates separated by the insulating dielectric. Okay, so we have the insulating dielectric, we have the insulating dielectric separating the. So if you really draw let's say if I want to draw a diode, okay, so if I just draw a diode probably here, okay, let's draw it fast. So you have got this, okay, and then you have got the depletion region. Let's say I'll just draw a standard depletion region. So this is your depletion region, okay, and this is the distance that I'm talking about, okay, and then let's say this is your p type, okay, and this is your n type. So you know these two P and N are the plates of the capacitor. Okay, so these two P and N will act as a plate of the capacitor. So might be this is this, might be this part is this. Okay, and this D is nothing but this distance. Okay, so we're talking about this distance is nothing but D. So that is nothing but the insulator or the dielectric that we have, because you know charges cannot flow here. Okay, so that's why it's acting more or less like an insulator. Okay, so that's the comparison that we can actually draw. Okay, and then you can consider this part as the area that we're talking about. Okay? This region, maybe, okay? This cross-sectional area that we have. So this is almost comparable to a, normal capacitor. Okay, and that is why it is called a variac. Okay, so this actually idea was quite interesting. Okay, and this capacitance is actually dependent on a number of factors. Okay, this capacitance is actually dependent on a number of factors. So it depends on the area, plate area, okay, plate area, okay, and then dielectric constant. So you basically have the dielectric constant, okay. So here also we are basically having the depletion region, which will define how much voltage should be there to break it. So it also has got a kind of constant involved there. Okay? So basically we have got the first term, which is the dielectric constant, okay, and of course the area distance between the two plates, okay. So distance between the between the two plates. So these are important factors. Whenever I'm asking a question or writing down the basics of variac, you can always explain these terms, okay. So we can actually number 4. So you know a capacitance will actually depend on the distance between the plates. So area, let's say it's fixed, okay, and if you're able to increase or decrease the area, you can change the capacitance. So if the area is reduced, if the distance between the plate is reduced, the capacitance will increase. Okay, if the distance is increased, okay, the capacitance will reduce. Okay, so what happens is that here also we can actually do the same thing. Okay, so the width of the depletion region, the width of the depletion region, okay, can be varied, can be varied, okay, by controlling the reverse bias, right? By controlling the reverse bias voltage, reverse bias voltage. Okay, so that is important. Okay, so this will be similar to changing the distance between the plates. This is similar to changing the distance between the plates in a capacitor. This distance between the plates in a capacitor. So you know, if we actually just consider it in terms of capacitor, we really understand that how does it look. Okay, so this is something which is similar here. Okay.
Sir.
Yeah.
Hello, sir. Sir,
Yeah.
if we increase the um, reverse bias voltage, then depletion region is increases width of the
Right.
depletion region.
Right.
Sir, then what happens, sir? Current is increases or decreases, sir?
So whenever we are increasing the width of this depletion region, that means effectively we are changing the value of D, right?
Yes, yes. Oh, yes,
So
yes, sir.
if we increase the value of D, that means the capacitance will actually reduce, correct?
Yes, sir.
So if we just consider a circuit which has got a capacitor and a resistor connected to it, we know how the current works, right? So if we have a circuit where we have capacitance and resistor, it won't be resistance anymore, it will be impedance, right?
Yes, sir.
So impedance is nothing but the effective resistance for that circuit. Okay. So what happens is if the capacitance reduces, the impedance also will basically reduce. Okay. So you know the relation of omega L and 1 divided by j omega c. Sorry, impedance increases. So I think this is something which is again important. If we consider the reactance of a capacitor and the reactance of an inductor, can someone tell me what is the reactance of a capacitor?
XC.
Okay, XC, correct. XC, we easily write it down. Okay, let me just write it down this way. Is equal to
C.
1 by omega c or omega c?
One by C omega, or sorry.
Correct, absolutely. Okay, so what we have is this. So let me just relate it with current. Okay, since you have asked this question, this is a good question. Omega c. Okay, so forget about this part now. So look into the capacitance now. Now what happens is I am increasing the width of the depletion region by increasing the reverse bias. That means D will increase. As a result, C will reduce. And in this case, if C reduces, the reactance will actually increase. Correct? So if the
Yes.
reactance increases, that means we can say effectively the resistance increases. So if the resistance increases, the current in the circuit will actually reduce. So if we just take these fundamental formulas, we can actually analyze what will happen to the current. So this is actually not discussed in this part, but anyway, this is very important to understand also. Okay. So let's just proceed. So how do I actually draw the circuit? I don't think we need to really draw it because I think it's quite obvious now. Okay? But then anyway, I'll just probably just draw a quick diagram here. Okay, and I'll just explain this in terms of maybe the voltage that we apply. So we have this circuit. Okay, so we have got the depletion region, we have got the P region, we have got the N region, and I want to connect it in the forward bias. So I'll just take this. I will or sorry, reverse bias, since we're talking about varactors. So P is connected to the negative junction, right? Okay, sorry, just rub this off. Okay, so I'll just connect it to the reverse bias. So this is my reverse bias, okay? And if the reverse bias is, let's say, around, let's say 3 volt, okay? So if the voltage is less, we have got a smaller depletion region, okay? And on the other hand, this is happens, I think this is something very important that practically we should look into the diagrams and try to realize the fact, okay? If we are actually having a voltage more, okay, we have got, let's say, now we are again connecting it in the, so if you are having a circuit like this, and let's say I'll increase the voltage a bit more, okay, let's say this is 6 volt. If we have this depletion region will be larger in size, okay, so this depletion region will be larger in size. So this is important here, okay, to understand that how does the capacitance actually vary, okay, with the size of the depletion region. So just look into this. C is equal to epsilon naught A divided by D. So here D is more, so the capacitance would be less. Okay, so here D is more. Okay, so this is the first case. This is the first case, let's say, and let's say this is the second case. Okay, so D is basically more in the first case compared to the second case. Okay, so if you take that into consideration, okay, what we have is the capacitance. So we know that this capacitance will be less. So typically, if you consider a diode, maybe a silicon diode, okay, this capacitance will have a value, let's say 5 picofarad. Okay, and if you're just considering this will actually have a larger capacitance. Okay, this will actually have a larger capacitance. Okay, so I will just write down this will be, let's say, 20 picofarad. So someone might tell you, or you might also get confused here, that the depletion
Sir,
region is large. Yeah,
sir, you write my sir. One the depletion region of one is smaller than depletion region of two, sir. Maybe
the
or
depletion
without
region
the
of
depletion.
one is greater, larger.
Not
Let me
no,
let me just explain this again. Okay, so look into this. What happens is here is this. Okay, let's say I have got a voltage of 3 volt. I will have some depletion region, and this is connected in reverse bias. Okay, so if
Yes,
the
sir. Yes.
voltage is more, the width
Will
of the depletion
increases.
region will increases. Correct? This is
Yes.
clear?
Yes, sir.
Right.
Yes,
So
sir.
if the width of the depletion region increases, the question is what happens to the capacitance, right? So if the width of the depletion region increases, that means D increases. So if D increases, capacitance will reduce, correct?
Yes, sir.
So if you are having a circuit where the voltage is 3 volt, the capacitance is, let's say, 20 picofarad. I'm just taking an example. If you are having another circuit where the voltage is 6 volt, that means the voltage is more. That means the width of the depletion region is more. That means the value of capacitance is less. So the capacitance will be effectively less.
In,
So it may be 5 picofarad. Is it clear?
yes, sir. Yes,
Yeah.
sir.
Yeah. So that's why like we have to just relate it with the original circuit. Okay. So I might ask you a some normal numerical problem, or might be a trick question, or might be a multiple choice question. Okay. So this is the beauty of Varactor. Basically, you can directly relate it with the capacitor directly. Okay, how does it behave? That's very important. Okay, what happens to if I just want to draw a figure? Okay, let me just draw probably a graph here so that we can actually understand that even more better. Okay, so what happens with voltage? What happens to the capacitance? So this is what is happening here. So if I just draw a graph, okay, so maybe I can just take the voltage here on this side. This is the CV characteristics, okay? So just like we have got IV characteristics, we can also have a CV characteristics, okay? Why? Because you are plotting a graph between capacitance and voltage, because capacitance is important here rather than the current, okay? So it's not IV, it's CV. So what kind of circuit we are actually having, depending on that, we can actually plot different kinds of graph. And here, CV characteristic is more important. Okay, and then we can actually take the capacitance. Okay, capacitance. Actually, this is something which is typical. This is seen practically. So I'm just putting the value as picofarad. Okay, so the range of capacitance that you get in a typical semiconductor will be in picofarad. Okay, so that is why I'm just writing this down in picofarad. Okay, so I'll just rotate this. Since we are using technology, so I have this benefit of doing everything in a proper way. Okay, so we have this, and if I actually now want to actually draw a graph, probably I can draw it this way. Okay, so probably I can draw it this way. So it will be like this. So you see, what does it mean? It means that if I increase the voltage, this is the reverse voltage. Okay, please remember this is connected in reverse bias. Very important. This is working as a capacitor only in reverse bias, not in forward bias. So if it's a reverse bias, I'm applying a reverse voltage. As I keep on increasing the voltage, the capacitance reduces. So if I increase the voltage, the capacitance will reduce. And this is actually having an exponential behavior. Okay, if you look into a typical relation of capacitor, this is a more or less exponential behavior. Okay, so this is a VCC characteristics. Okay, so Varactor voltage capacitance characteristics. Varactor voltage, or let's say I'll just write on VVC characteristics. So you say, just like you say IV characteristics, you also have a VC characteristics. Okay, sticks. Okay, so this is the VCC characteristic. It looks like an exponential curve. So if the voltage is less, let's say this case, the capacitor is more. Okay, how less? Let's say this might be a value of 0.1 volt. Okay, if this is 0.1 volt, you might be getting a capacitance of, let's say, around 14 picofarad. Okay, maybe approximate. I'm just giving an approximate range. Okay, on the other hand, if I just increase the voltage, and let's say I'm giving a voltage of 4.5 volt, okay, then the capacitance that you might get might be approximately 2 picofarad. This is a typical range in which it works. Okay, so whenever you are going to purchase any kind of any kind of electronics, okay, a capacitor or resistor, and if you are buying it from a legitimate buyer, he or she will also give you a data sheet. Okay, and those data sheet will actually have the information of how your electronic gadget that you've purchased actually works. Okay, so if you're purchasing a capacitor, they'll probably give you these kind of graph, that you are actually having a circuit and you are connecting the circuit with it, okay, and you are applying this voltage. This is the capacitance that you can expect, and based on this you can actually design your device, okay. So you know, these things are practical, these data sheets, actually people work on that and they do use it, okay. So what can we actually use to manufacture Varactor, okay. So I think this is also important, and I know some of my sheets have crashed, so but anyway, we are recording it, so we already have the record. So I'll actually upload it. The other two lectures I'll upload it today. Okay, so you'll get those two lectures. Okay. So Varactor diodes are manufactured. Okay, I think I should write it down. This is important because reality is important with gallium arsenide. So a typical semiconductor that is being used for designing Varactor is gallium arsenide. Okay. So if you ask me that are these values valid for gallium arsenide, the answer is yes. Okay. So this is more or less taken from something like gallium arsenide. Okay. And you know, since it is a capacitor, it should also work on. It should not be damaged by frequency. Okay. So if you are having any kind of electronic circuit, okay, you are applying some kind of frequency. So usually omega, okay, in a home typical household power supply, the frequency is 50 hertz, okay. But then these gallium arsenide, if you are using a circuit, you're tuning the circuit, the frequency variation can be anything, okay. So it has basically got a very high operating frequency, okay, operating frequency, okay, and it is as high as 1000 gigahertz. This is as high as 1000 gigahertz. So it can actually operate at a very high frequency. Okay. And having said that, it's talking about, we are talking about the voltage capacitor characteristics to understand that how does it behave, how does the capacitance change with voltage. It's not that it won't have any IV characteristics. It will definitely have IV characteristics, because whenever you're reverse biasing, still there will be some kind of current acting on it. Okay. So if you are asked to draw the IV characteristics of any kind of diode, the behavior or the image that you will have is more or less the same. Okay. So it's not going to change much. Okay. It's not going to change much. And we are probably going to use the same kind of figure in IV characteristics. Okay. So if we consider, since we are using gallium arsenide, okay, the values of the reverse voltage or the forward bias voltage might change a bit, okay, but then more or less the behavior will more or less remain the same. Okay, so it's not going to change much. Only the current range and the voltage range will actually change. Okay, so you basically have a forward bias like this. Okay, and if we are considering a reverse bias like this, right? So this is your Zener breakdown or avalanche region. Okay, these regions will be there, still will be there. Okay, this is just a region. It's not that this region will only be there for a Zener diode. Okay, it depends on any kind of diodes. You are applying a reverse voltage, you are increasing the voltage to a very high value. At some point there will be a breakdown, there will be a large current which will actually flow, and as a result of which you are basically going to get a breakdown, and that is nothing but the Zener breakdown region. Okay, usually in an avalanche breakdown we have got more current. Okay, so we are going to get higher voltage and we are going to get a breakdown at a higher voltage. Okay, so avalanche breakdown and Zener breakdown, the difference also we are going to see when we are going to look into a simple typical IV characteristics, okay, of Zener diode. So that is something which we are going to check into this later. So this IV characteristics I'm not going to explain, because I think last time also we did it. Okay, but then I think last time it crashed, so I don't have the saved images here. Okay, this is today. Yeah, so the last time it crashed, so it did not got saved somehow, but we already know about the IV characteristics. Okay, so just refer to that. It is going to be the similar kind of figure. Okay, but then the range is going to be more or less similar like a Zener diode. Okay, so we're just going to look into that later. Okay, so what are the applications of this particular Varactor diode? Okay, so maybe I can just look into the applications. I'll just clear this part. Okay, don't need it. Okay, erase. Okay. So applications, okay. Now we know how does it look, and then what are the applications. It is actually used in microwave circuits, okay. So the variation of current can be done using these kind of circuits, okay. Microwave circuits. In general, diodes are a very reliable device, okay. Some of the applications of a general diode might be to stop reverse flow of current. For example, let's say you have got a solar panel, and then you know that when basically light falls on this silicon wafers, okay, it generates charges, okay, and these charges can get stored in a battery for later use, and that is how a solar panel works. But then there are also chances that the charge may flow from the battery back to the solar panel because they are connected, okay, by a wire. So I need to stop it. How do I stop? We actually use devices like diodes. So diode is basically a unidirectional device. It allows current to flow only in one direction. So it can flow, the current can flow from the solar panel to the battery, but not from the battery to the solar panel. So you know, these diodes are very reliable devices. So they usually don't fail if you are using the correct voltage that has been advised to use. Okay, so that's very important. So that is why it can also be used in something like a resonant tank circuit. So tank circuit, okay, tank circuit is nothing but an LC circuit, okay, and this is something you might have already studied, okay, in your degree. So tank circuit, there also, if you actually want to have a capacitor, this Varactor diode can play the role of a capacitor, okay. Varactor diode, okay, Varactor diode can be used as a C or a so this Varactor diode can be used as a capacitor in a tank circuit, okay. So that is also important. And then in radios and televisions also nowadays they are used, okay, and televisions. You might ask, how do I use it in radios or television? So you know, in those old radios, nowadays we are doing it digitally, but then in those old radios, you are basically using a knob which you can actually rotate to tune the circuit, okay. Once you've tuned it, different station gets in, okay. So you know, frequency of 102.5 or big FM 94.5 or red FM 92.3, you know these things, right? These are all dependent on frequency at which they are transmitted. So you need to vary the frequency. You know that if you have a circuit, let's say an LCR circuit, the inductance is omega L, there is a frequency term. The capacitance is omega C, there is again a frequency term. It's comparatively easier to vary the frequency in a capacitor. So whenever you have those knobs, you are tuning those knobs, you are actually changing the frequency. And based on that, you are actually getting the, yeah. So what happens effectively is you are changing the reactance of the capacitor. Okay, you're changing the frequency, you're changing the reactance of the capacitor. Okay, so based on this, you're actually tuning into a particular radio station. Okay, so this is exactly how it works. Okay, we can actually use a varactor to use in these kind of devices also. Okay, it can also be used in microwave receiver. Okay, but let me just give you 4 points. Maybe I can talk about radio frequency phase shifter. Okay, so shifter. So, you know, if you're actually going to change the behavior of a circuit, you can actually change the phase, do play with the phase shift. Okay. So if you want to play with the phase shift, actually you can use the varactor. Okay. So these are some important applications of varactor, which is also important. Okay. So, you know, the varactor basically works on the reverse bias mode. Okay. So if you just look into this entire idea of a varactor, okay, you know that this actually works in the reverse bias mode, okay, and then in the forward bias it usually does not it works, but then it works as a normal diode, and then that's not how it's used, okay. And the depletion region will act as an insulator, okay, and that is actually the region which actually controls the capacitance value, not the area, not the value of epsilon naught, okay. So if you increase the reverse bias, you basically get the variation in capacitance.